Hello, in this lesson we're going to learn how to verify trigonometric identities. Verifying identities is one of the most important skills in trigonometry because it teaches us how different trigonometric functions are related to one another. Rather than showing and solving for an unknown angle, our goal will be to show that two expressions are equivalent. As you will see, verifying identities requires algebra skills, knowledge of the fundamental identities, and a little creativity. Let's get started. Our objective in this lesson is straightforward. We want to learn how to verify trigonometric identities. Along the way, we'll discuss several useful strategies, examine multiple examples, and learn how to recognize when techniques such as factoring, common denominators, converting to sines and cosines, or rationalization can help simplify an expression. By the end of the lesson, you'll have a toolbox of techniques that you can use whenever you encounter a trigonometric identity. Before we begin verifying identities, it's important to understand the difference between a conditional equation and an identity. A conditional equation is true only for certain values. For example, sine of x equals 0 only when x is equal to n times pi, where n is an integer. Since the equation works for some values of x, but not all values, it is called a conditional equation. An identity is different. An identity is true for every value in its domain. For example, the equation sine squared x equals 1 minus cosine squared x is true whenever both sides are defined. Notice that we're not looking for specific values of x. Instead, we're showing that two expressions represent the same quantity. Although verifying identities may seem similar to solving equations, the process is actually quite different. Success comes through practice and familiarity with the fundamental identities. There is no single recipe that always works for every identity. However, there are several useful guidelines. First, work with only one side of the equation at a time. In most cases, it is best to start with the more complicated side. Second, look for opportunities that factor expressions, combine fractions, or simplify denominators. Third, look for places where you can apply the fundamental trigonometric identities. Often, one identity can transform an expression into something much simpler. Fourth, if you're stuck, try converting everything into sine and cosine. This is often the most reliable strategy because all trigonometric functions can ultimately be written in terms of sine and cosine. And finally, don't be afraid of experiment. Sometimes a path that doesn't seem to work still provides insight into what might work. Let's verify our first identity. Notice that the left side appears more complicated than the right side, so we begin there. The first step is to use the Pythagorean identity. Since secant squared theta minus 1 equals tangent squared theta, we can replace the numerator. Next, we use the reciprocal identity to rewrite 1 over secant squared theta as cosine squared theta. Now we use the quotient identity to rewrite tangent squared theta and sine squared theta divided by cosine squared theta. The cosine squared factors cancel, leaving us with sine squared theta. Since this matches the right side of the equation, the identity has been verified. Notice that we never manipulated both sides simultaneously. Instead, we simplified one side until it became identical to the other. One of the interesting aspects of trigonometric identities is that there is often more than one correct solution. In this example, we verify the same identity using a different approach. Instead of using the Pythagorean identity first, we begin by splitting the fraction into two separate fractions. Next, we use the reciprocal identity to simplify each term. This gives us 1 minus cosine squared alpha. Applying the Pythagorean identity transforms the expression into sine squared alpha. Even though the steps differ from the previous slide, we arrive at the same conclusion. This illustrates an important point. There is often more than one valid path to a correct verification. For the second identity, the right side is more complicated, so we begin there. After obtaining a common denominator, simplifying the numerator, applying the Pythagorean identity, and using the reciprocal identity, we arrive at 2 secant squared alpha, which matches the left side. The identity is therefore verified. When other approaches fail, converting everything to sine and cosine is often a powerful strategy. In part A, we rewrite tangent as sine divided by cosine and cosecant as 1 over sine. The sine factors cancel, leaving 1 over cosine, which is secant. Thus, the identity is verified. In part B, we again rewrite tangent and cotangent using sine and cosine. After finding a common denominator and combining the fractions, the numerator becomes sine squared plus cosine squared x. The Pythagorean identity tells us that this quantity equals 1. From there, we simplify and obtain secant x times cosecant x. This exactly matches the right side of the identity. Whenever you encounter an identity involving tangent, cotangent, secant, or cosecant, converting to sine and cosine is often a good first strategy. This example introduces an important technique called rationalization. We begin with the right side because it is more complicated. The denominator contains 1 minus sine x. To simplify it, we multiply both the numerator and denominator by 1 plus sine x. This creates a denominator of 1 minus sine squared x. Using the Pythagorean identity, we replace this with cosine squared x. The expression can now be separated into 2 fractions and simplified. Eventually, we obtain secant x plus tangent x. Since this matches the left side of the equation, the identity is verified. Rationalization is a technique that students often learn in algebra, but it is equally useful in trigonometry. Most of the time, we simplify only one side of an identity. However, occasionally it is useful to simplify both sides independently. In this example, we begin with the left side. Using the Pythagorean identity, we replace cotangent squared theta with cosecant squared theta minus 1. Factoring the numerator allows us to simplify the expression to cosecant theta minus 1. Now we turn to the right side. Separating the fraction into 2 terms gives 1 over sine theta minus 1. Recognizing that 1 over sine theta is cosecant theta, we again obtain secant theta minus 1. Since both sides simplify to the same expression, the identity is verified. This approach can be particularly useful when neither side clearly simplifies directly to the other. Let's finish with 2 examples that frequently appear in calculus. In part A, we start with tangent to the 4th power. We factor it as tangent squared x times tangent squared x. Then we replace 1 factor of tangent squared x using the Pythagorean identity. Distributing the remaining tangent squared factor produces the desired expression. In part B, we begin with the cosecant to the 4th power times cotangent. We rewrite 1 factor of the cosecant squared x using the Pythagorean identity. After distributing, we obtain the expression on the right side. These examples demonstrate why mastering trigonometric identities is so important. When you begin studying derivatives, integrals, and other calculus topics, you'll frequently use these same techniques to simplify expressions and solve problems. This concludes our lesson on verifying trigonometric identities. Thank you for watching, and I'll see you in the next lesson.